So I will just start from the very basics. I will speak about slopes of lines, and that's a thing that you already know about. So let's go through that, and we know that if we have a coordinate axis system, x versus y, y versus x, right, we can draw straight lines on this coordinate system, and for each straight line we can define something called a slope. So I have drawn two straight lines here on the page, and the way we try to define the slope of these straight lines is use the formula m is equal to y2 minus y1 by x2 minus x1. That is the symbol of slope. This guy m is the symbol of slope, and this is the equation. And speaking in terms of trigonometry, that shows you tan theta, where theta is the angle that the line makes with the horizontal axis, the x-axis. For example, here if you look at the green line, and if I draw the horizontal axis over there, it will make a theta green with that horizontal axis. If you take the blue line, and if I were to draw horizontal over there at the blue line, it will make an angle theta blue with this horizontal line, and the slope of this blue line will be measured in terms of tan theta b, and for the green line it will be tan theta g. And the idea of tan is essentially opposite by adjacent, so the same idea works. So say for example you take two vertical lines. I draw two lines parallel to the y-axis like this, and maybe another one somewhere else, another brown line, let us say somewhere here, and these two lines basically can be used to figure out the slope of the blue and the green lines. All you have to do is find out what this point is. This is the first point that we are talking about. Find out what that point is. This is the second point that we are talking about. And then for the green line, find out what is the value of change in x coordinate to the change in y coordinate. So if you try to find out the change in y coordinate, that's probably shown by this entire height, delta y, and the change in x coordinate is shown by the distance between these two lines, delta x, and the ratio here will give you tan theta g, which is also the slope of this green line, and the same thing for the blue line, right? And slopes, you know that slopes of lines can be plus, they can be minus, they can be high, they can be low, they can go even up to infinity. So which line has got an infinite slope? Right, nice. So a line that is along the y-axis has got infinite slope, a line that is along the x-axis has got zero slope. Right, so infinite slope will not be used much, but zero slope will serve another purpose, and you need to keep that fact in mind, that we can draw a line that is along the x-axis and it will have zero slope. Right, and then let's go to slope of curves, and this is the place where we were in the previous class, slopes of curves. And the general idea is that in order to find out the slope of a curve, all you have to do is draw a tangent. So if I ask you the slope of a certain curve, you have to draw a tangent to the curve at the desired point. So you should also ask at which point. So suppose you have a set of coordinate axes x, y that looks like this. You have y and you have x, and there is a curve that we are talking about. We are probably talking about this curve, right? And we want to find out the slope of this curve at a point like this here. So maybe I mark a point on this curve A. So all you have to do is draw the tangent at A, and maybe the tangent at A will look like this, right? So if you draw the tangent at A, find the slope of that tangent, that will give you the slope of the curve at A. And I take a different point somewhere here like B, and maybe I draw a tangent over there at B, and it gives me the slope of the curve at this point B, right? But this is not something that we would like to ordinarily do. We would not like to get the equation of a curve, then draw the curve on the xy plane, and then at the desired point draw a tangent and then find out the slope, so that when I give you a different point, you again have to go into the same kind of thing. You have to draw the curve, draw a tangent there, and then find out the slope of that tangent and find the slope of curve. So we would like to have something which is more mathematical, something more something more easier to do than drawing a curve and then drawing a tangent and So although it seems like an easy thing to do, we can always draw a curve, we can always draw a tangent, it takes a lot of time. So in our quest to do it mathematically, what we have done is this. Now give me just a moment. Yeah. So what we have done is this. Suppose I take a set of coordinate axes, y versus x, and on that set of coordinate axes I've got a curve, and I ask myself that if I take a certain point A on this curve, somewhere to the left hand side, somewhere here, right? So if I take a point A on this curve, and if I have to maybe choose another point on the curve, B, somewhere here, let us say, so I am free to choose B anywhere. So I could choose B at maybe a location called B1, or maybe I could choose B at B2, and then maybe I could choose B at B3 to the extreme right, So I could take this point B anywhere on the curve, and I've taken 3 different points. And I ask myself, if I join this point A to this point B, wherever I have taken it, so AB1 is one possible straight line, AB2 is another possible straight line, AB3 is another possible straight line, can any of these straight lines give me the slope of curve at A? So no. Cool. So if I draw any of these 3 straight lines, I'm not going to get the slope of the curve at A. Fine, I can take this straight line AB1, and maybe I can take another straight line that's AB2. I'm showing you all these straight lines to show you that they won't give me the slope of the curve at this point A. But then, can I do something else? If I'm free to take B point anywhere, then where should I take this point B intuitively, so that it gives me, so that if I join A and B, that gives me the slope of curve at A. So maybe if I take just a very small part of this curve, say I just draw this section AB1 of this curve on a graph below, you will be able to see that the section will look something like this here. This is the y-axis, this is the x-axis, and I'm talking about maybe this kind of a curve, right? And here is on the extreme left, somewhere here is the point that I had chosen as A, and maybe I take a point B somewhere on the highest part of the curve here, somewhere close to that, and I draw this line AB, right? And I see that the slope of that line is nowhere near the slope of curve at A. Fine, cool. But what if I keep on moving this point B closer and closer to A? Right, I can always do that. I can move this point B, so B happens to be on the top. I can shift it to the left, to more left, more left, more left, and still keep it on the curve. And when B gets to maybe some point here, let me draw that position. So when B gets to this blue marked point, and I draw a line joining A and B at that position, maybe the slope of that line is very close to the slope of the curve at A. If not exact, maybe approximately. The line that we have drawn, the orange line that I have drawn here, or maybe I'll turn it into blue or something. So the blue line that I have drawn here is not exactly a tangent. If you zoom into this picture, you will see that of course it intersects the curve at 2 different places. So it's a secant. So when can I approximately say that it's a tangent? Right, so if I keep on pulling B closer and closer and closer and closer to A, then maybe if the spacing between A and B is very, very, very small, I can say that it's approximately a tangent. Right, and how good a tangent is, so we are now trying to compare 2 methods. We are now trying to compare a mathematical method where I'm trying to take a point B which is extremely close to A, and then try to do some kind of calculations. On the other hand, the other method which we have is actually physically drawing it and then drawing a tangent. So we have 2 methods. One is drawing, where you have to keep in mind that the accuracy will be based upon the accuracy of your drawing. The second is more mathematical, where if you go close to A to a certain amount, the accuracy is guaranteed because you're doing calculations. Right, so in the drawing the tangent method, if you are using a thin tip, then your answer will be more accurate than my answer if I was using an insanely thick tip or something. But then when we are using the mathematical method, your answer and my answers will match, because we will be doing everything only in terms of equations. And in maths, what we can do is we can say that the distance between AB goes to 0. So what we can do is we can try to find a formula in terms of the length AB. And if I want to say that this point B is extremely close to A, all I have to do is, in the final formula which I get, which is in terms of the length AB, I have to put AB is equal to 0. So if I put AB is equal to 0, then I am essentially saying that A and B are the same points. And then whatever equation I have got, and after I insert AB is equal to 0, will actually give me the precise equation of tangent. Let's say that there is a certain curve that looks like y is equal to x plus 2 into x minus 1 into x minus 3, let us say, some curve. So I have chosen this format because it helps me to understand where the roots of this curve are. So this curve will intersect the x-axis at 3 points, minus 2, 1 and 3, and I will be able to get a rough feel of this curve in all the different parts. So let me just take one x-axis somewhere and see the nature of this curve as I go from one value to the other. So I will get three distinct regions. Right, so I will get three distinct regions here. So one region will be to the left of minus 2, the other region will be in between minus 2 and 1, and the third region will be to the right of 3. And maybe I will get a third region here somewhere like this. So this is x is equal to minus 2, this is x is equal to 1, this is x is equal to 3, and let's say what happens to the curve, or not what exactly happens to the curve, but the sign of this y variable. What's the sign of y when I have x less than minus 2? So let's have a look at the first term. First term will be negative. Suppose you take x is equal to minus 5. Then the first term is going to be negative. The second term, all three are negative. Yes, so the curve will be negative here. And then when I move into the second zone here somewhere, you will see that only this term will change sign, x plus 2 term. So now that term will become positive. So the curve sign here in this region will be plus. Right. In the third region here, so the curve will look something of this kind. It will go up, then it will come down, then it has to go down again, then it has to go up, and something of this kind. Now let us try to focus on this part of this curve. That's somewhere between minus 2 and 1, because that shows us a nice upgoing curve or something, or maybe beyond 3. It doesn't matter, because the shape will be like this, and then it will keep on going up all the time, and on this side it will keep on going down all the time. Right. So let's focus on some part of this curve, and let us say that there is some point over there, some point A, where we want to find the slope of this curve. Right. So we will use this equation, and to show you that this equation shows us a curve, I have drawn the curve here, and now I'm going to use this equation and this point A to get to a formula to find out the slope of this curve at point A. So let us take this curve again, and what we usually do is let's just draw that curve approximately. So it was like this in some portion, and there was a point A chosen here. So I choose a point A, and then I will take a point B somewhere here. So I'll take it sufficiently far apart, but I'm going to use the condition mathematically that the distance between A and B is 0. So that I will put afterwards, after I get everything, and I draw a line at A like this, a vertical line at A. So that goes and hits the x-axis somewhere, and I can draw a similar vertical line at B that will go and hit the x-axis somewhere else, so something of this kind. and these two lines are going to I can also draw two other lines from A and B that go and hit the y-axis at some points, and I can label maybe this point A as x0 or xa, right, and the y coordinate as y0, and the spacing between A and B as delta x. Yeah, so this spacing here is probably delta x. So this point is x0 plus delta x, a small increment over the previous value, and consequently what is happening is that the y coordinate of B is more than the y coordinate of A, or it has changed at least. So if the y coordinate at A was equal to y0, then the y coordinate at B will not be y0, it will be y0 plus something, and I'm calling that y0 plus delta y. So the idea is that you are standing at some point A on the curve, you have a x coordinate x0 and a y coordinate y0, you go to a different point B. Now B could be on the right hand side of A, or B could also be on the left hand side of A, both are allowed, right? So the change in your x coordinate will be labeled as delta x, where delta x can be plus or minus. If delta x is plus, that means the change is plus in sign, and the final x value will be more than the initial x value, so the final x value has to be here, somewhere here, right? This change can also be negative, which will mean that the final x value has to be less than the initial x value, so you will be standing somewhere to the left hand side of A, somewhere here, right? And similarly, we can have an appropriate sign for even delta y. So we say that at B, the y coordinate is y0 plus delta y, where delta y can have a sign that is plus or minus, it doesn't matter, right? So if the sign of delta y is plus, that means B is going to be higher up than A. If the sign of delta y is minus, B is going to be lower down than A, right? So we will keep in mind that these terms delta y and delta x can have signs, but whenever we will try to write them in our equations, we will always write x0 plus delta x and y0 plus delta y to signify a change. And then the slope of this line that joins A and B is, easily, we have done that before. Slope is yb minus ya divided by xb minus xa, and I can write that as delta y divided by delta x, and I want to find this value. I want to find the value of slope delta y by delta x when B is extremely close to A. So I want to find the value of this entire number delta y by delta x as the values of delta x tend to 0. So this will be the symbol of saying that B is extremely close to A, and wherever this guy delta x appears in the equation, we will put delta x as 0. So if I put delta x as 0, you will see that B will fall back upon A. So we are not going to speculate that here, because there may be, if you have a curve that is like this brown line here, let us say, right? So for this brown line, even without having any delta x, you can have a delta y. So it is entirely possible to have a change in the y coordinate without even having a change in the x coordinate. Yeah, so there may be. So it depends on the exact nature of that equation that has been given to us. So for this example, we have taken an equation of this format, so we'll go ahead with that. So y is equal to x plus 2 times x minus 1 times x minus 3, and first is what I want to do is I want to open it, I want to expand it so that it looks like one single equation. So how will it look like? There will be a x cube term, then there will be a x square term that will come from, I think it will be easier to open it bracket by bracket. So x square minus x plus 2x, so plus x minus 2 into x minus 3, and this will give you x cube, and you will have minus 3x square plus x square, so minus 2x square, and then you will have minus 2x minus 3x, so minus 5x, and then you will have plus 6. I hope I have done it right. So how can we check if we have done it right? If we insert any of these three values, we should get a 0. So minus 2 will give us, so x is equal to minus 2 in this equation will give us minus 8, minus 2 into 4, minus 5 into minus 2, and plus 6. So this is minus 8, plus 10, plus 6, which is a 0. Right, and in the same manner, if x is 1, on the right hand side, what do I get? 1 minus a 2 minus a 5 plus a 6, which we know is 0. And if x is equal to 3, we can say the first term will be 27, the second term will be 18, the third term will be minus of 15, and then you will have plus 6. So 33, that gives you a 0. Yes, so we have done it right. So this is the equation of the curve. Now A lies on this equation, A lies on this curve. So A should be able to satisfy the equation of this curve. So when I look at the equation of this curve for point A, I can write for A, y naught is equal to x naught cube minus 2x naught square minus 5x naught plus 6. For B, the equation which I can write is y naught plus delta y, because the new y coordinate is y naught plus delta y, and that will be equal to x naught plus delta x whole cube minus 2 times x naught plus delta x whole squared minus 5 x naught plus delta x plus 6. Yes, and then we try to figure out what's the value of delta y, because our end aim is to get this ratio delta y by delta x. So the way to do that is, we will take the second equation, which is y naught plus delta y is equal to everything. From that we will subtract the first equation. So on the left hand side we will be left with delta y, and on the right hand side we will have some kind of terms, but we will try to divide every term by delta x. So on the left hand side we will then get delta y by delta x, and on the right hand side again we will get some expression. And then finally on the right hand side we will insert delta x is equal to 0. Right, so let's just try to do it. So what you will get on the left hand side is delta y. So let me also say that that's 1 minus 2 or something, or 2 minus 1 or something. So let me call this equation equation 1, and let me call the second equation equation 2, and what I'm going to do here is 2 minus 1. So when I do a 2 minus 1, on the left hand side I'm ending up with delta y is equal to, you will have x naught plus delta x whole cube minus x naught cube. Right, so that's the difference of first two terms. Then in the next two terms I can take minus 2 common, and you can say you will have x naught plus delta x whole squared minus x naught squared. Yes, and in the third term I can take minus 5 common, so minus 5 and x naught plus delta x minus x naught, and the last term 6 will go off. Yeah, so let's do this job of evaluating the right hand side now. You will get from the first term, we will have to open it up physically, you know. So a cube plus b cube plus 3a square b plus 3ab square minus x naught cube. Then the second term I'm going to write down, so minus 2 times you will have x naught squared plus delta x squared plus 2x naught delta x minus x naught squared. And the third term I can straight away cancel out that x naught, and I will have minus 5 delta x. So you will see that what's happening here is, on the left hand side I've got a delta y, but on the right hand side from the first row x naught cube will cancel out. In the second row, so let me throw away that x naught cube. In the second row, x naught square goes off, and the terms that are left now will be delta x cube plus 3x naught squared delta x plus 3x naught delta x squared from the first row minus 2 times of delta x squared plus 2x naught delta x for the second row and minus 5 delta x for the third row. And then you divide every term by delta x. So delta y by delta x will be delta x squared plus 3x naught squared, and you see that in this term delta x squared will be left over here, but there will be some terms like this where delta x term will not even be present. And then the third term will give you 3x naught times delta x minus 2 delta x plus 2x naught minus 5. And then the next thing that we write here is a bit mathematical. So we have invented a new symbol, and we say that we will try to write an expression of this kind: lim delta x tends to 0 delta y. You have seen this? Yeah. So this guy shows you, or it actually asks you, what is the limiting value? What is the limiting value of the fraction delta y divided by delta x under the condition that delta x tends to 0. This is the question that we are being asked when we see this kind of an expression. And the answer to this is obtained by inserting delta x is equal to 0 in every term on the right hand side. So this guy, the first term will go off. It won't even remain there because it's delta x squared. This second term will remain. So I will have a 3x naught squared. Then the third term will go off. Yes, minus 5. That's good. So we have ended up with this expression, and we knew the value of x naught. We knew the value of x naught because we knew where this point A was. The point B was some arbitrary point that we were trying to take, and we have taken this point B extremely close to A, so the exact coordinates of B are not known or not necessary. But from the last step that we have done here, what we have ensured is this, that the x coordinate of B is the same as x coordinate of A. That means in the last step we are saying that B is the same as A, right? But otherwise everywhere we have used information about the exact information about A. So we know what is x naught. We can insert it here and we can find out the answer. And the left hand side shows you basically, so it is asking you the limiting value of the fraction delta y divided by delta x. So you know that this guy shows you a slope. So we are essentially talking about the slope of the curve when this point, we are talking about slope of this straight line AB when this point B coincides with this point A, and that will be the tangent drawn at A. So this is the slope of tangent drawn at A, and this also is then the slope of the curve at point A. Right, so this is one basic thing, but then we have done it for just one point A. What if you have to do it for another point C on the same curve? So what I'm going to do is, on the same curve I'm going to take a point C somewhere, and I'm going to say that this point will be some xc and the y coordinate will be some yc. Then essentially to find the slope at C you will have to repeat the same process, where instead of x naught you are going to put xc. Yeah, because we had xc here, and so everything will be repeated in exactly the same fashion. But in the last step, instead of getting x naught square and 4x naught, you are going to get a 3xc square minus 4xc minus 5. Yeah, so that gave us the idea that we can remove this x naught from this equation and we can replace it with a general x. And we can say that whichever point you want to find the slope at, you just insert the x coordinate of that point. So let me just take the equation of this curve, y cube minus 2x square minus 5x plus 6. So therefore, slope of curve y is equal to x cube minus 2x square minus 5x plus 6 is given by the expression (3x square). So I will write limiting case delta x tends to 0, delta y divided by delta x is equal to 3x square minus 4x minus 5. And then what we said was that we don't want to write this over again and again. This is a huge expression for us to write. So instead of saying limiting case delta x tends to 0 whenever delta y by delta x to be found out, we will write this entire thing as dy by dx. So dy by dx, and we have given this guy a name, limiting delta x tends to 0, delta y by delta x is dy by dx, where dy is a small change in y and dx is a small change in x. The interpretation of dy by dx is the rate of change of y with respect to x, right? And this is a fraction. This is a fraction. You can call it a fraction, fraction, or you can maybe call it a rational number. Whatever you want to call it, it is that exact thing, fraction or maybe a rational number, because the numerator is a number and the denominator is a number. It's of the form p divided by q, right, where p and q are both numbers. And dy and dx will be very small as they can be. So maybe x can be around 10 to the power minus 18 or minus 30 or something. Y can also be that small. Right, so one question that enters into the mind is, if I take dx so small and if I take dy so small, will the fraction dy by dx have a physical meaning? Yeah, both are very small. Yes, both tend to 0. No, it depends on who is the smaller one, whether dy is the smaller one or dx is the smaller one. But surely we can definitely find a value for the fraction. For example, if I take something like 10 to the power minus 5 divided by 10 to the power minus 8, I will still get a number that's 1000. So even though I have two numbers that are infinitely small, okay, these are not infinitely small, I have two numbers that are very small, their ratio is a decent number, right? So these are the numbers that we are accustomed to in our everyday life. Or maybe if I have like 10 power minus 28 divided by 10 power minus 30, so two infinitesimally small numbers, but I'll still get 100, right? So maybe what happens is that this number shows you the distance traveled by an object, and this number shows you the time in which that distance was traveled, and then you get the speed as maybe 100, which is not entirely something out of this world. 100 meter per second is also definitely possible, right? So a ratio of two numbers, both of them very small, still makes a lot of sense, right? And in physics, wherever you have to measure the rate of change of one variable with respect to another variable, you will keep in mind that that is represented by this guy dy by dx, right? But until now what we have done is we have only found out this thing for a specific curve, right? And the moment the equation of curve changes, we will have to redo this entire process. So that part was also done. So people before us, they have done this for a large number of curves. They have taken varying equations, and they have found out that there is a certain pattern. And then when they did this entire process for a large number of curves and they hit upon the pattern, they coded everything into some kind of formulae. And so these days, those are the only formulae that we have to keep in mind. And if you know those formulae, you can easily work around any function that you get. So before we go to that formulae, I will have to introduce another notation. So here, if you remember, I told you that this guy dy by dx is actually a fraction. It's a rational number, right, where the numerator is a small number and where the denominator is a small number. And if you have one number by another number, the answer will be a number. The answer won't be an equation of this kind. It won't be a function of this kind, right? So clearly, if I keep on doing this process for any point, any specific point, I'm not going to get an answer like this. So how can I end up with an answer like this? To get an answer of this kind, they have defined something called a differential operator. And so we have something called a differential operator. Have you heard of operators in maths? Yes. So those are the operators that we are talking about, plus, minus. The only thing is, when you use this operator, it's called the plus operator. It is a binary operator, which means it needs two numbers to operate upon. So you need to have one number on one side and another number on the other side. And if I give you these two numbers, you know exactly what to do and the answer. Give me some more examples of maybe binary operators. Minus, multiplication, division, all of them are binary operators, right? Can you give me examples of some kind of operators that operate on single numbers? They are called unary operators. Unary operators. Powers, I'm not sure whether they come under the category of operators. Yes, factorial. Then maybe a square root, maybe a modulus, right? So all of these operate upon single numbers and they give you another answer which is also a number. Similarly, this guy will be an operator. So we have defined a new operator which we call d by dx operator. This is called the differential operator. Differential operator. It operates upon functions. So it operates upon functions. Yes. So it can operate upon any function of x, and its answer will be usually another function of x, where gx will represent the rate of change of fx with respect to x. So as a very simple example, suppose I give you a function. Example, I give you a function y is equal to 4. First of all, is this a function? No, why not? Yeah, but we can still say that it's a function and it's a constant function, right? So we say that it's a constant function, y versus x. This is y is equal to 4. It doesn't vary with x. And suppose I ask you the slope of this function. Your answer will be intuitively 0 because it's along the x-axis. The answer is 0. But suppose we followed the same procedure that we have done for the previous curve. So suppose I label this point as a and I take another point as b, and I take the spacing between a and b as delta x naught, and I try to find the slope of line which joins a and b, and then I insert in that final equation that delta x is equal to 0, I will still get a 0. Right? The intuitive idea here being that when I find out d by dx of a function, I get the rate at which it changes whenever x changes. Now, whenever x changes, a constant function doesn't change. So the rate of change is 0. And that's the first formula that you should keep in mind, that d by dx of a constant is 0. Right. Second thing that we will learn is straight from this equation. Suppose this equation, the equation of the curve which I have, I multiply it throughout by a term, say around 4. Right. So I multiply this whole equation, not the LHS, the RHS of this equation by 4. So that every value of y becomes 4 times the previous value of y. Now when I do this entire calculation, what will I get? So the first one, the first equation, I will have 4 with every term on the right hand side. And in the second term also, the second equation also, I will have 4 with every term on the right hand side. When I do a 2 minus 1, I will have an extra 4 multiplied to every term here on the right hand side. And finally, when I get the answer, the answer will also have a 4 multiplied to every term. So that gives us another insight. We say that, okay, if there is a constant that is multiplied to the function, and I want to find the derivative of that, so maybe I have something like d by dx of some constant c times fx. So what I've done is I have taken a function fx, multiplied it by a constant c, and then I'm trying to find out the slope of this entire thing. That can still be done if I take this c outside, and then I find the slope of fx first, and then I multiply every term of that with that constant. Right, so we will have c times d by dx of fx. So these are the first two intuitive rules, and the others will follow easily based on these rules. So let's go to those formulae. Right, so this thing, I think in all the thing that we have done now, and all these things that we have done now, only this part was new to you, right? This part. So this is the basis of all the things that we know as calculus. Small changes. Right, and then after seeing this, I think you will know exactly where all the formulae are coming from. So this process has been done over again and again for various different kinds of functions. So you know that there can be algebraic functions, there can be trigonometric functions, there can be exponential functions, inverse trigonometric functions, logarithmic functions, and so on, right? So for each one of them, this process has been done and we have got certain answers. And the next thing that we will do in this class is have a look at some of those formulae. So the first formula that you should know is this. When the differential operator acts upon a constant function, you get a 0. So, I will henceforth just say that d by dx of c is 0. So the second formula is whenever you have a d by dx of c times fx, that's c into d by dx of fx. Any constant can be brought outside the differential, and you can find out the slope of the remaining function, and then to every term you can multiply that constant. That is what this whole thing says, Then suppose you have d by dx of x raised to the power n, and this is something that you know. Tell me. N times x raised to the power n minus 1. So maybe if I ask you what is d by dx of x cubed, correct, 3x square. What is d by dx of 1 by x? Minus 1 by x square, correct. And maybe if I ask you what is d by dx of root x? Mm-hmm. Correct. Yes. And what is d by dx of, let's say, 1 by root x? So x raised to the power 3 by 2. Yeah. So this is how this formula works. D by dx of x raised to the power n. Let's have a look at something else. So suppose I have got a large number of terms added up. Suppose I have got something like d by dx of c x raised to the power n. What will that become? Correct. And then let me add up a few terms. Let me say I have d by dx of c times f of x plus g of x plus some h of x. What will that become? So c times d by dx of f of x plus c times d by dx of g of x plus c times, yeah, h of x. This is what we have, right? Then let's say we have something else. We go to trigonometric formulae. Yeah, let's go over to trigonometric formulae. So there is something called d by dx of sine x, let us say. That's, yeah, that's cos x. The thing is, there is something called Taylor series expansion. Yeah, Taylor series of sine x when expanded about 0. So you don't have to worry about these words, but you should know the series. When expanded about 0 is sine x is equal to, it starts with a x, right? So x minus x cube by factorial 3 plus x power 5 by factorial 5 minus x power 7 by factorial 7 plus x power 9 by, no, you're not supposed to know how this guy comes in, but then you just should know this expansion, right? And there is a certain expansion of cos x also. So cos x is 1 minus x square by factorial 2 plus x power 4 by factorial 4 minus x power 6 by factorial 6 plus x power 8 by factorial 8 minus, and so on. The series goes on. So the key thing that you should keep in mind is both sine and cos will have the first term plus and thereafter alternatively. So the first term for both sine and cos will be plus. So it will be plus x for sine and plus 1 for cos. And keep in mind that sine will have all the odd powers, cos will have all the even powers. And there is something called e raised to the power x, where e is the e here is the Napier's constant. So e raised to the power x is something like 1 plus x square by factorial 2 plus x cube by factorial 3 plus x power 4 by factorial 4 plus x power 5 by factorial 5, no change in sign here, plus up to infinity. Right, the above two series are also up to infinity. So from this, if you just accept that these series are things that are there, which are established, then you will be easily able to understand why d by dx of sine x becomes cos x. So let's have a look at d by dx of sine x. So therefore something like d by dx of sine x will be d by dx of 1 minus x cube by factorial 3 plus x power 5 by factorial 5 minus x power 7 by factorial 7 plus x power 9 by factorial 9 minus so on, and the series will go on. And when you try to find the derivative, what happens is, do it for the first term, then the second term, then the third term, right? So how much is d by dx of, this is not 1, the first term is x. So how, 1, yes, so 1, then the next term, correct, and then you will have 9x power 8 by 9 factorial and minus and so on. And then if you know the definition of this guy, the factorial thing, so this is 3 into 2 into 1. 3 into 2 factorial, and the 3 will cancel out. 2 factorial. Similarly, this guy will be 5 into 4 factorial. So 5 will cancel out, and you will get only x power 4 by 4 factorial. So you get something like 1 minus x square by factorial 2 plus 4 by factorial 4 minus x power 6 by factorial 6 plus, so now I think you've got a hang of it. So that is cos x, right? Similarly, if you do it for cos x, let's just have a look at this expression here. If you do it for cos x, you are going to get 0 for the first term, correct, x, then it will be correct, x5 5. Correct. And then you see that every term will have the opposite sign of what we have in sin x. So here we had x as plus, here we will have x as minus. Then the next term, minus x cubed by factorial 3, here we'll have plus x cubed by factorial 3. And so, because every term has got a minus sign, I will take the minus outside, and then inside the bracket I will get the same series as sin x. Minus sin x, yes. Minus sin x. Then you have got something like d by dx of e power x. E power x itself. Yes, so if you have a look at this expression, you will understand why. The first term will give you a 0, second will give you yes, so that's the first term. So have a look at the first term. This is the first term which you have got after using d by dx of x. And then x, so that's this second term. So each term will be shifted, right? So each term, so x cubed by factorial 3 will be x squared by factorial 2. So this term will be shifted here, this term will be shifted here, this term will be shifted here, and so on. So e power x will remain e power x. Then there are other formulae that you should know. D by dx of tan x is, yes, not minus, that is cot x. So this is secant square x. Then d by dx of cot x no, you have to just keep in mind that it is so you see that we have two functions, tan, cot, and then there we have secant and cosecant. So the usual way in which we write them is sine, cos, tan, cot, secant and cosecant. So keep in mind that these two will interchange amongst themselves when we are talking about differentiation or even integration. Right, so tan will be associated with secant, cot will be associated with cosecant. Yes, yes, they are. So d by dx of cot x will be minus cosec square x. The only thing is there will be a new minus sign, that's all. And then you will have d by dx of secant x, and that goes to secant x tan x. Okay. Right, some reason, we don't have to get into that. Then you will have d by dx of cosecant x, and have a look at, yeah, yes, with a minus sign, cosecant x, cot x. Right, so it's the same pattern which is being followed in these trigonometric formulae. Then you should know something about ln x. D by dx of ln x gives you, yes, that's 1 by x. Right, so you will have all these formulae. And what else is there? Yeah, you should know now two important rules. In fact, three important rules. The first one is called the product rule. So let's go for the product rule. Product rule say, yeah. So this is d by dx of u into v, let us say. Or maybe, okay, so it's called the uv rule, where I will make a note that u is like f of x and v is like some g of x. So yeah, you tell me, what is this? Correct. So we keep it in mind in terms of u and v. So this is u dv by dx plus v du by dx. Much easier to keep in mind like this. Right, then there is a rule that is division rule, but to understand the division rule properly, we should go for first of all the chain rule. So chain rule is interesting, and chain rule is a rule where you should give a lot of energy to. So what does the chain rule say? Suppose you have a function y that is maybe a function of x. Right, so let's say it is something, say 3x square plus 5x minus 10, something of this kind, some function of x. And x itself is not an independent variable. So when we are speaking about physics, or when we are speaking about the calculus thing, we are talking about independent variables and dependent variables. So let's say even x is not independent variable. X in fact depends upon some variable t. So x is some g of t, some other variable. Maybe it is sine t or something, who knows. Or maybe it is something like 3t plus 5, right? Some kind of a function. So the idea here is that t is the real independent variable. When I make a change in t, a change is made in the value of x. And if I make a change in the value of x, a change is made in the value of y. So there is a chain kind of, t leads to x and x leads to y. And what I'm interested in asking is, what is the rate of change of y whenever I change t by a certain amount? Yes. And I'm interested in the rate of change of y with respect to t. So keep in mind that the rule is very simple. The rule says that if you have to find out the rate of change of y with respect to t, then that's essentially trying to find out dy by dt, where this is like a fraction, right? So what we will do is we will take a value of t, that's t naught. So I'll just explain the process in brief. You have got a value of t, that is t naught, and at this value x has got a value, that is x naught, and y has got a value which is y naught. Now what you do is you make this guy t naught increase by a certain amount, change by a certain amount. So the new value is t naught plus delta t. When you do that, when you change the value of t by a certain amount, the value of x also gets changed by that same amount. So you get x naught plus delta x. So where delta x is a small change which is made in the value of x, when a small change of delta t is made in the value of t. But when x changes, even y should change. So the new value of y that I get is y naught plus delta y. Because x changes, even y changes. And what I want to do is I want to find out the ratio delta y by delta t. And I want to find out this ratio when the values of delta t are very small. So let's throw away this guy for a moment. Let us only try to find out what is this ratio delta y by delta t. So I know that if I am dealing with pure numbers, then delta y by delta t can be represented as delta y divided by delta x multiplied by delta x by delta t, where if these are just numbers, then delta x can cancel out and I will get back the same kind of fraction. But then if I also try to write this condition that delta t is very small, extremely small, then I can change the format of these expressions on the right hand side. I can say that then I'm dealing with something like dy by dt, and that's dy by dx multiplied by dx by dt. So the idea is that here also they are numbers. Here dy is a number, a very small number, dt is a very small number, dx is a very small number, and if they are numbers, then dx can cancel out. Right, so I know that this can happen if dy and dt and dx are all small numbers, or maybe even if they are big numbers, still that formula is true. But then when they are small numbers, we have defined something called a differential operator. So then what we do is we speak in terms of that differential operator, and we say that suppose I want to find out the rate of change of y with respect to t, then I should find out the rate of change of y with respect to x and multiply that by the rate of change of x with respect to t. So therefore d by dt of y can be written as d by dx of y multiplied by d by dt of x, or you can equivalently say dy by dt is equal to dy by dx multiplied by dx by dt. So this is the so-called chain rule, and it can work for a large number of parameters. So maybe I take a different example where y is a function of a, and a is a function of b, and b is a function of c, and c is a function of d or something, and I should not use f everywhere. I should use maybe f1, f2 and f3 and f4 and so on to show that they are all different functions. Right, so I have all these things, and I can still find out the rate of change of y with respect to c or maybe d as dy by dd, and I will have dy by dA, dA by dB and dB by dC and so on. Right, so the series goes on and on and on and on. So keep in mind chain rule, but where is the chain rule used? Right, so let me show you the use of chain rule, and then let me show you one easy way in which to implement it and find the answers in a very fast manner. So let's say I ask you what is d by dx of sine x, sine 3x now. Tell me. So you will be tempted to say this is like cos 3x. Yeah, but then yes, of course, this is a part of the answer, but the answer doesn't end here. There is something else to it. And the reason is we only know the formula to find out d by dx of sine x. So we only know how to find out the rate of change of sine x whenever x changes. But here what happens is, if you have a look, I'm trying to find out the rate of change of sine of 3x whenever x changes, and I will not be able to get the same answer. Right, so this is a very easy example. It is, we can see this example in two different ways, but I'm going to show you maybe the chain rule way. And in the chain rule way, we say that let this guy 3x be equal to t. Then I was originally trying to find out what is d by dx of a function y, where the function y is sine of 3x. This is what I was originally trying to find out. Right, and I have labeled this guy 3x as t. So now y becomes sine of t, because t and 3x are the same things. And I know that t is equal to 3x. And this is the format that I have just now described to you for chain rule. When y is a function of t and t is a function of x. So you make a change in x, t changes. And if you make a change in t, then y changes. So if I have to find out dy by dx here, then I have to simply find out the rate at which y changes whenever t changes, and multiply it by the rate at which t changes whenever x changes. Right, you understood till here? Yeah. So then I think the answer is very clear, Ananya. All you have to do is find out dy by dt, and that is something we know, because if I try to find out dy by dt on the left hand side here, I'll have to take the derivative on the right hand side also. And d by dt of sine t is cos t. That's the same expression as this expression, except that in place of x I'm saying t. Right, so that won't change the way the expression works. So this is sine t multiplied by what is dt by dx here, using this expression. Sorry, this is cos t. So sorry. So this is cos t multiplied by, what is dt by dx from here? Three. So the answer is finally 3 cos t, and then you can resubstitute for t. So you can say this is 3 cos 3x. Done. This is the final answer. Right, so this is how chain rule will work. So it seems a long thing, so we have to assume some things in between and then try to do it, but then I'll show you a shortcut, as I said. But that shortcut after another example. What if I have something like, so let's take another example. Let's say I have something like d by dx of e power 5x minus 8. Can you do this? So what we do here is, we will assume this guy to be some y, and y is e raised to the power 5x minus 8, and that's your clue, because you know a formula for e power x, but you don't know a formula for anything else. So that's your clue that you should take this guy as t or something. So let t be equal to 5x minus 8. Then you have y is equal to e power t, where t itself is 5x minus 8, and you want to find out dy by dx, which is dy by dt multiplied by dt by dx. Then when you find out dy by dt, you will have to use the first expression. How much will that be, dy by dt? That's e power t itself multiplied by, what is this guy, dt by dx? 5. Yes, you're right. So this is 5 e power t. Right, so this is 5 e power t, and then you change back. You say this is 5 e power 5x minus 8. Done. So that's the final answer here. Let's take one more example of chain rule, how it works. Let's say I have got y is equal to a sine omega t plus b cos omega t. Let us say some expression where a, b and omega are constants, and I want you to find out what is dy divided by dt. So the long way to do this is y is equal to, you can write it as y1 plus y2, let us say, where y1 may be a sine omega t, or you don't even have to do that. You can just say that let this guy omega t be something called u. So let omega t be something called u. Then you have y is equal to a sine u plus b cos u, and where u itself is omega t. Right, so dy by dt is what you want, and that is dy by du, because y is now a function of u, multiplied by du by dt. And dy by du will give you a cos u minus b sine u, and all that multiplied by du by dt will give you omega. So the final answer will be a omega cos, and insert for u, so omega t minus b omega sine omega t. Right, fine, you've got a hang of it. Give me an answer to this. What is d by dx of sine t? See, this guy which I have here inside the sine function, and this guy which is outside, they are not the same. So there is a shortcut of chain rule, and this guy, the answer to this will lead us to that. So here you have to keep in mind that t may be a function of x. There are only two things that can happen. So case 1, t does not depend upon x. This is case 1, and maybe case 2, that t depends upon x in some manner. Is there anything else possible? If t is independent of x, let's say case 1. So what if I'm talking about case 1, So t is independent of x. So t is independent of x. It implies that if x changes, will t change? T does not change. If x changes, t does not change. And then in that case, will sin t change? Sin t also does not change. So d by dx of sine t, that tries to measure the rate at which sine t changes whenever x changes. What should it be? Tell. See, we are interested in the rate at which sine t changes. We are not interested in the actual value. So the actual value of sine t will be something. Let's say it is some number. We don't really care about that number. What we care about is, if I change the value of x, does that number change? No. So what should be the rate of change of sine t with respect to x? 0. That's the answer. Okay, so case 1, if t is independent of x, then I can say that this term is a constant. That brings us to the first rule. Right at the top here, d by dx of a constant is 0, and it was 0 precisely because when I made a change in x, the constant will be unaffected. Right, so you have understood the first case when t does not depend upon x. So now let's go for the second case. So case 2 is t depends upon x. T depends upon x. So if t depends upon x, then I will have to write down this d by dx of sine t as maybe d by dx of y, where y is equal to sine t and t is some kind of function of x, but we don't know this guy. This has not been given, but they still want us to write the answer in some manner. So what we say is, now I want to find out dy by dx, because I have to find out now dy by dx, where y itself is equal to sine t, right? So dy by dx will look like dy by dt multiplied by dt by dx. So dy by dt is easily found using this expression. What is dy by dt from this? Cos t. Yes, nice. Cos t multiplied by, here I will be at a loss because I have no clue what this guy t is, or how does it look like. Is t an algebraic function of x, or is t maybe a trigonometric function of x, or maybe it's an exponential function of x? I have no clue at all. Right, so since I have no clue, I cannot do anything about this term, but I'll have to keep this term as it is to show somebody else that this t will depend upon x, and that has to be inserted here. And then what if this guy t in the end does not depend upon x? Then how much will be dt by dx? 0. That will lead us to the first case. If t is independent of x, then the answer was anyway 0. Okay, so it's always safe to write down this answer as, so therefore d by dx of sine t is expressed as cos t multiplied by dt by dx. That's the safe way to write the answer, where what you're doing is you are saying that the first term is anyways expected, right? So the sign changes to cos, we know that that's a standard formula, but then t might vary with x. So I have to multiply everything by that term dt by dx, where if t does not depend upon x, then the second term will become 0 and I will anyways get a 0, which was expected. Right, and this is the shortcut for chain rule. Why am I saying this is the shortcut for chain rule? You see, if I give you some expression like what I did earlier, the first one was sine 3x. So let me take that example. So I had given you an earlier example about d by dx of sine 3x. So in your mind, you make the connection between this guy 3x and that guy t. And you say that, okay, this looks like this boxed formula. Right, so what I have to do is, first see, for any chain rule problem, whenever you see that the variable inside and the variable with respect to which I have to find out the derivative. So here I have to find out the derivative with respect to x. If I write d by dt, I have to find out the derivative with respect to t. If I write d by du, I have to find out the derivative with respect to u. So that should be amply clear. So if the variable inside and the variable with respect to which I have to find the derivative are not the same, then it's a chain rule problem. Then what you do is you first find the derivative as usual, like you would have if this was just sine x. If it is just sine x, it will give you a cos. So the first term will be cos of 3x. And then what you do is you find the derivative of the term inside and you multiply it. So you have to find out d by dx of 3x. And how much will that be? D by dx of 3x. 3. So the answer is 3 cos 3x. So you see that we have avoided. So here also the answer was 3 cos 3x. But that was after assuming something as t and then finding out all those chain rule things. So chain rule helps us to understand, right? But then there is a shortcut to chain rule which we can use, and we have to use it in this manner. So suppose I give you the next one. I gave you the next example as d by dx of e power 5x minus 8. So you keep in mind that there is a more basic function. So you have to keep in mind what is the outermost function. So the innermost one here is 5x minus 8. So you have one inner function, and then outside that you have a function like e power something. So you have e power something, and that something happens to be 5x minus 8. So start from the outermost one. E power something. What does e power something give you? It gives you e power to the same thing. So e power the same thing, and then move inside in steps. So you will have d by dx of 5x minus 8. Right, and you keep it in multiplication. So how much will be d by dx of 5x minus 8? 5. So 5 e power 5x minus 8. Done. This is what you got here. Where are we? Somewhere here. 5 e power 5x minus 8. Right. And so you can do all the others also like that. But let me give you a slightly more complicated example. What you have? What if you have something like d by dx of ln of cos of 5 e power x minus 3. How will you do this? So first try to identify how many different levels of functions do we have, right? Correct? Correct. So the three functions which you have identified, the first is this innermost guy, then cos of something, and then ln of something, which is the outermost one. Ln. So start with the outermost one. What does ln of something give you when you take the derivative? 1 by x. So the answer here is 1 by cos of 5 e power x minus 3. So ln of something will give you 1 by that thing. So here you had ln of this entire thing, that will give you 1 by that entire thing. But it doesn't stop here. You have to find out d by dx of cos of 5 e power x minus 3. So now we are on the second level. Now what does cos of something give you? Minus sign, correct? So you have minus sine 5 e power x minus 3 divided by, and this cos anyways is here, so I'm saying this is divided by cos of, or if you want me to keep it separate, I'll do that. So this will be 1 by cos of 5 e power x minus 3, and cos of something gives you minus sine of that very thing, so 5 e power x minus 3, and then because the term inside the cos function was not a simple x, we will have to find out the derivative again. And this is in multiplication, so you have to keep in mind that, and I'm showing you using pink brackets, that this term is in multiplication. And now how will you find out this answer? No, we are done with the substitutions. We have used the substitutions to learn about the chain rule, but now that learning is done, we are on the shortcut. So see, you will have to first of all break this into two parts. So it is d by dx of first term minus d by dx of the second term, and the second term will give you a 0 because it's a constant. So it's only d by dx of, so I will just try to write this down. This is d by dx of 5 e power x minus d by dx of 3, and the 3 term will give you a 0, so that's gone, correct? And then what does that term give you? D by dx of 5 e power x. So whenever you have a constant multiplied to, yes, waiting, 5 e power x, okay. So therefore the final answer is minus sine 5 e power x minus 3 divided by cos of 5 e power x minus 3 multiplied by 5 e power x. Yes. Correct. You can say minus tan. Yes, that's right. So if you want to write it in a very short form, minus 5 e power x tan 5 e power x minus 3. Done. So this is how the chain rule works. Any issues with the chain rule? No. Okay, cool. So after the product rule and the chain rule, let us go to the division rule. Yes, the quotient rule. So you have heard about it. I also hate that rule, but I'll just show you the final formula. I always just use the product rule, and I will show you how. So d by dx of something called u by v, right? And let me show you how to arrive at the final expression. So in books they will give you a final formula, but I'll show you how that thing comes, and it's very easy if you have understood the product rule and the chain rule, right? So suppose I use the product rule here. I can say this is like d by dx of u multiplied by 1 by v, where I can treat u as the first function and multiplied by this entire thing as the second function. So now this is like first function into second function, so I can use the product rule. So it looks like u d by dx of 1 by v plus 1 by v d by dx of u, right? So now we will have to use chain rule here, because what will happen to this term is, this term looks to me like d by dx of v raised to the power minus 1. So let's have a look at what happens here on the right hand side. So suppose you have got some term, like suppose I ask you what is d by dx of 3x plus 5 raised to the power minus 2. What will you do? Let's use the chain rule itself. Okay, so first you make the connection that this is something raised to the power minus 2. What does that give you? It will give you no, something raised to the power minus 2. If you try to find out the derivative, what should it give you? So you ask yourself the question, what does d by dx of x raised to the power minus 2 give you? Correct. So like exactly here this equation gives you d by dx of x to the power minus 2. It gives you minus 2 x to the power minus 3. In the same manner, this equation will give you minus 2 3x plus 5 raised to the power minus 3. But then you will have to spot the difference, and the difference is here it was simply a x raised to the power minus 2. Here it is 3x plus 5 raised to the power minus 2. So you know that the thing that you are trying to take the derivative of, that's not just a function of so it's not just x, it is in fact a function of x. So chain rule will apply. And what do we do in the chain rule after we do this? See again, you break it up into two functions. The inside one is 3x plus 5. And then outside that is that 3x plus 5 whole raised to the power minus 2. So here the function is in two levels. The outside one is something raised to the power minus 2. And that something itself is 3x plus 5. Right, so how do we deal with it? How do we actually deal with it? We will deal with it in an outside to inside fashion, and we'll keep on going inside. And every progressive derivative will be multiplied. So the outermost one is something raised to the power minus 2. It gives you minus 2, that something raised to the power minus 3. So we have dealt with the outside function. So now we need to put a multiply d by dx of the function that is one level inside. What is that? 3x plus 5, that's all. And what will that give you? This 3x plus 5 will be 3. So correct, right? You got this? So now you have a look. You have got some kind of a function v, but that v itself has been raised to the power minus 1. So first is you throw away from your mind the fact that v is a function. You deal with it like it was x raised to the power minus 1. What will it give you? Minus 1 by v square then. Yes, because of course, if you think in terms of x, it will be minus 1 by x square, but now because we have v, it will become minus 1 by v square. But the process won't stop there, because this v will have some kind of a function of x. So what should we do next? Multiply here. dv by dx, that's all. Right, so that is what we have to do, and we are at a loss. We cannot find out this term because we have no clue about the exact format of this function v. But if the exact format of this function v is known, then we will be able to find out this term also, like we did here on the right hand side. Right, so it was like d by dx of v raised to the power minus 2. So it was minus 2 v raised to the power minus 3 into d by dx of v again. and you got this is whole answer, right? So what you will get here now is, so this whole thing looks like u times minus 1 by v square dv by dx plus 1 by v times du by dx. And you can take the LCM. So the LCM is, see, in the first term you have v square in the denominator, in the second term you have v in the denominator. So correct. So you can say minus u dv by dx divided by v square. So I'm keeping the v square in the denominator, plus v dx divided by v square. And how the books they show you the formula is then and because this term has a minus, I want to keep this term first. So what the books will show you is this: v du by dx minus u dv by dx divided by v square. And how to keep that in mind, they will say denominator times d by dx of numerator minus numerator d by dx of denominator divided by denominator squared. Right? So this is the so-called quotient rule. But then you will see that what we have done is we have just used product rule and we have used chain rule. Yeah. So I guess that's the theory of differentiation. Now I've got some very nice practice sheets. I will be sending you the practice sheets, and if you do them, you will be thorough with all these initial formulae plus also chain rule and the product rule and the quotient rule. They have some really nice problems on chain rule.